Hello viewers, today we will be discussing Curie temperature and magnetic domain, and in here we will be extensively discussing ferrimagnetic material, response of temperature on magnetic material, concept of magnetic domain, what is hysteresis and coercivity, concept of giant magnetic resistance, that is GMR, and magnetic storage. Ferrimagnetic materials. As we discussed in our previous presentation that the ferromagnetic materials are characterized into two subcategories, that is antiferromagnetic materials and ferrimagnetic materials. We have discussed antiferromagnetic material, and similarly ferrimagnetic materials can also be presented in terms of the interaction of the spin magnetic moment between the neighboring atoms, and the spin magnetic moment here are such that the strength of the magnetic moment in one atom is higher than the strength of the magnetic moment in the other atom. Usually the ferrimagnetic materials are ceramics which show permanent magnetization. Now, the macroscopic, as we discussed, the macroscopic characteristic is same as ferromagnet, but the distinction lies in the source of magnetic moment. The most basic example is ionic cubic ferrites. These ferrites are having composition of MFe2O4, where M is any metallic element. Now, the prototype ferrite is Fe3O4, which is called magnetite. Now, the formula may be written as Fe2 plus O2 minus or Fe3 plus 2 O2 minus 3. So, both Fe2 plus and Fe3 plus coexist in plus 2 and plus 3 valency. So, both of them contribute towards the spin magnetic moment, whereas oxygen ion, that is O2 minus, does not have any magnetic moment. Now, the magnetic moment is 4 and 5 Bohr magneton for Fe plus 2 and Fe plus 3 respectively. There also exists antiparallel spin coupling between Fe ions or the iron ions in the composition of magnetites. Both the magnetism arise due to the net spin moment of Fe2 plus and Fe3 plus ion in the composition. Now, if we look at the picture in this slide, then we can see the arrangement of ions in the lattice of the magnetite. Here you can see the cubic ferrites have inverse spinel structure. So, the spinel structures are closed pack structures of O2 minus ion stacked together, and there are two positions where Fe ions are located. So, some of them are present in a location which make tetrahedral structure, and some of them are present in a location which make octahedral structure. So, the tetrahedral structures are having coordination number 4, whereas the octahedral structure are having coordination number of 6. Now, half of the Fe plus 3 ions are making tetrahedral structure and the other half is making octahedral structure, but Fe plus 2 ions are located only in the octahedral position. That is why all the ions that are Fe plus 3 in nature, their net magnetic moment is 0, because the Fe plus 3 ions present in the octahedral position, they are aligned in the up spin direction, and the Fe plus 3 ions which are present in the tetrahedral position, they are present in the down spin magnetic moment position. So, because of these type of arrangement, the net magnetic moment due to Fe plus 3 ion is 0. So, the contribution comes from Fe plus 2 ion, which is either in the up direction or in the down direction. So, the net magnetic or the net magnetization is due to the Fe plus 2 ions in this magnetite materials. So, now if we present the behavior or the nature of magnetic moment in this material due to Fe+3 and Fe+2 ions, then because we have isolated them in terms of their position in the lattice. So, the Fe+3 ions which are present in the octahedral position, let us say they are in the up spin direction, then the Fe+3 ions which are present in the tetrahedral position, they will be aligned in the down direction. So, there is a net cancellation of the magnetic moment. That is why the net magnetic moment due to Fe+3 ion is 0, whereas Fe+2 ions, they are present only in the octahedral lattice position. That is why there is a net magnetic position which are here in this table presented by up arrows. So, in cubic ferrite, Fe+2 can be replaced by other metals such as nickel+2, cobalt+2 or gadolinium+2 with different magnetic moment. Now, a mixture of divalent metal can also be a ferrimagnet such as manganese, magnesium, Fe2O4. These are called mixed ferrites. Hexagonal ferrites are also available, and the formula is Ab12O9, where A is a divalent metal and B is a trivalent metal. Some of the common examples are PbFe12O9 and Ba Fe12O9. Garnets are also ferrimagnetic materials. The example of garnets are Y3Fe5O12, and the saturation magnetization is less than ferromagnetic materials. Since these are ceramics, they are very good insulators. So, we can use these ferrimagnetic materials where we do not want the electric current to flow, but we want the magnetic field to be present because of the magnetic behavior of the materials. Now, we would understand the effect of temperature on magnetic material. As we increase the temperature, the lattice vibration of the material will also increase. Now, since the magnetic dipole rotates freely, so if we increase the temperature, the rotation of these magnetic dipoles will increase and the randomization of the magnetic moment will occur. So, because of that, it will counteract the coupling in ferro, ferri and antiferromagnetic materials even in the absence of magnetic field. So, because of this counteracting of the randomization to the interaction of the spin between the neighboring atoms, there is a decrease in the saturation magnetization in ferri and ferromagnetic material, and the saturation magnetization is maximum at absolute 0 temperature. So, as you can see in the graph in this particular slide, there is the saturation magnetization versus the temperature plot of pure iron and Fe3O4 is presented. Here, as you can see, with the increase in the temperature, the saturation magnetization is decreasing, and the temperature at which the saturation magnetization is decreasing is called the Curie temperature, which is represented by Tc, and above Tc, ferri and ferromagnetic materials behave as paramagnetic materials. So, for the iron and Fe3O4, the Curie temperature is around 800 and 600 degrees Celsius respectively. Now, in the previous discussion, we have talked about the magnetic domain. These are the regions in the magnetic materials where the magnetic moment is aligned in a particular direction. So, in ferro and ferrimagnetic materials, below Curie temperature, small volumes having all the dipoles oriented in the same direction will form domain, and these domains are separated from each other by domain walls where the dipole moment changes gradually. So, the magnetization of solid is sum of magnetization of each domain. For non-magnetized material, the magnetization of domain cancels out. That is why the net magnetic moment will become 0 and they will behave as non-magnetic material. Now, if we study these magnetic materials in terms of the magnetic domain, then we have to represent the internal magnetic field strength with respect to the variation of external magnetic field strength. So, B and H relation is not proportional for ferro and ferrimagnetic materials. For non-magnetic materials, at H is equal to 0, B is equal to 0, but as we increase H, B also increases slowly and it reaches saturation at some point. So, if we plot a curve between B and H, then we will see the variation of the internal magnetic field strength with respect to the external magnetic field strength is not linear, but the characteristic feature that we can obtain from this curve is the magnetic permeability, and we will find that the magnetic permeability is dependent on the external field strength. So, at H is equal to 0, the permeability is called initial permeability and is represented by mu E, which is the material property. The maximum value of B is saturation flux density, which is represented by Bs, and the corresponding magnetization is saturation magnetization. Initially, domains are randomly oriented, hence net magnetic moment is 0, but as we keep on increasing the external magnetic field strength, the magnetic moment in individual magnetic domain will align in such a way that at the saturation position the net magnetic moment will be in the direction of the external magnetic field, and hence the saturation is obtained. Now, if we study the behavior of the internal field strength with respect to the external field strength, then we will find that it starts from 0 and then it reaches a saturation point. Let us say that saturation point is S, and if we trace back the curve by decreasing the external magnetic field strength, then we will find that it is not tracing the same path in which it went and reached the saturation point. It is coming through a path in which, if we observe the internal magnetic field strength when the magnetic field is 0, it is not completely 0 for the internal magnetic field strength. There is some amount of magnetic field strength left for the material, and that is called remnant flux density, which is observed when we retrace the curve in the opposite direction. And if we want to obtain 0 magnetic field strength for the material, then we have to go further in the negative direction, and at a particular external magnetic field strength we will find that the magnetic field or the internal magnetic field strength has become completely 0, and that particular magnetic field strength is called coercive force, which is a negative quantity to achieve the 0 internal magnetic field strength. And if we keep on going back with a higher external magnetic field strength in the negative direction, then in the negative direction we will reach to saturation, and if we keep on increasing, then internal magnetic field strength will not increase. But if we again come back in the positive direction, it will take a different path and it will intersect to the y axis in a point which will be having opposite magnitude to that of the remnant flux density that we discussed a little while, and that remnant flux density is equal and opposite to the remnant flux density that we got when we were tracing from positive to the negative direction. And if we keep on increasing the magnetic field strength again in the positive direction, it will go in a different path and it will reach saturation. Now, if we observe this particular curve we will find that this is a symmetrical curve, but it has some amount of hysteresis. That means it retains some amount of magnetic moment even if we are going back to the same magnetic field strength that we started with. This symmetrical feature of the hysteresis curve can be obtained in different way without even attaining the saturation. As you can see in this particular picture, that the curve shown by ML is a hysteresis curve where we have not yet achieved hysteresis, and this curve, hysteresis curve, can also be achieved without even going to the saturation point. We can stop the magnetic field at any point and we can retrace, and we will still achieve a hysteresis curve. So, the hysteresis behavior of the magnetic material is a signature of ferromagnetic and ferrimagnetic materials. Now, using this concept of the hysteresis by the magnetic material, we can use or we can apply them to construct giant magnetic resistance devices. So, giant magnetic resistance will be helpful in retaining higher amount of data, or the memory density for the devices will increase because by using the giant magnetic resistance. So, what is giant magnetic resistance? It is basically the change in the electrical resistance in presence of external magnetic field, and that change is called the magnetic resistance. So, this is obtained when we have thin film of magnetic and non-magnetic materials, and the electrical resistance decreases significantly in presence of magnetic field. So, what we do is that we take thin films of magnetic and non-magnetic materials, and in between we have spacer materials. So, by controlling the film thickness and the spacer thickness, we can control the ratio of magnetic resistance. One such device is by using iron, cobalt and nickel iron as the magnetic and non-magnetic material for the GMR devices, and here the spacer material could be chromium or copper. Now, when magnetic field align, the magnetic moment in successive films decreases the resistance of the devices, because for metal, if we consider the resistance of the metal, then it is because of the scattering of the electron from the different lattice side. But if we consider the electrical resistance due to the spin of the electron, then in that case the spin of the electrons might scattered due to the flip of the skin, but otherwise they will not be scattered from the lattice side. So, in that way there would be no heat loss due to the transport of the spin information from one point to the other point. In that way we will achieve the flow of current in the material without even any dissipation of heat. In that way these devices are better than the normal electrical devices, because they do not dissipate any heat from the devices. And these giant magnetic resistance can be used for recording devices, where we want to record some amount of information for our future application. So, one such device is magnetic hard disk, and another example is magnetic tape. So, in magnetic hard disk there is a circular disk which is rotating at some higher speed, that is some speed around 5400 to 7200 rpm, and they, while rotating, there is a reed head which is a inductive reed head which basically reads the rotating disk, and in that way it can extract the information that is stored in the magnetic hard disk. And these magnetic hard disks, their storage capacity is something of the order of 1 terabit per inch square. Now, the next one is tape storage, which is also a device which can be used for storing information, and here the storage density is little less than the hard disk storage devices that we discussed, and it is of the factor of 100. So, here the tapes are wound around a reel and it rotates using a motor which moves past the read write head. Typically, the speed at which it moves is 4.5 meter per second to 10 meter per second. So, the storage media is basically particulate of magnetic materials that have dimensions of 10 nanometer, and these particulates are either ferromagnetic materials which are in needle shape or hexagonal shape, and ferrimagnetic materials which are tubular in shape. So, these particulates, they will be present on top of a polymer material. So, the tape is a polymer material in which the magnetic particulates are embedded, and these particles are present in such a way that they are oriented in a preferential direction, and the alignment is in the direction of motion of tape. So, two magnetic state, that is up and down spin, record the data in the magnetic domain. In this magnetic tape, the storage density is 6.7 gigabit per inch square, and it can be achieved by using barium ferrite medium. So, today what we discussed is, we extensively discussed the ferrimagnetic materials and the origin of their magnetic property. Then we discussed the effect of temperature on different magnetic materials, especially the ferromagnetic materials. Then we discussed the role of magnetic domain towards magnetization of the material, and we studied the hysteresis behavior in magnetic materials and how these hysteresis behavior will help us understanding the GMR devices, that is giant magnetic resistance based devices, which are the future of storage and electrical transporting materials for any kind of device application that we want to study in the future. And then finally, we discussed the different recording medium in which we can use the magnetic material to record the data for the future applications. Hope you would have liked today's session. Thank you very much.